Hello everybody, this is Dr. C. Today's lecture will focus on salt solutions. Doesn't sound very exciting, but we do have to know how to calculate the pH of these because depending on what the salt is, sometimes salt solutions will be neutral. Let me say that again. Some salts dissolved in water will be neutral, some salts dissolved in water will be acidic, and some dissolved in water will be basic. Okay, and we need to be able to distinguish those and also calculate the pH. So what we're going to do in this lecture is we are going to compare three salts. Okay, sodium chloride, and these are aqueous solutions. Sodium fluoride, oops, and okay, I'll write it like this just so you can see it, and ammonium chloride. Now you should be able to recognize salt solutions. We covered those last semester, and we have seen many examples of ionic compound salts. So what we're looking for is typically a metal cation and potentially a non-metal anion, but some anion. They might be polyatomic anions like nitrate or sulfate. So we could have something like sodium nitrate, so NO3 minus. And we talked about polyatomic ions last semester as well. But let's now put those in the mix right now. Sodium fluoride, Na plus, F minus. Now usually the cation is a metal cation, but not always. And in this case we have the ammonium ion, and that is a polyatomic cation. And if you're thinking about weak bases and all the things we've covered so far, you might recognize this as the conjugate acid of ammonia. Okay? We talked about ammonia being a weak base. And when ammonia accepts an H+, we produce its conjugate acid, and that would be ammonium. All right, so that's going to be important as we go through this lecture and discussing salt solutions in terms of, in general, what is their pH, acidic, basic, or neutral, and then how do we actually calculate that. Okay, so let's look at these three salts. And we know that a salt like sodium chloride, when it dissolves in water, these are soluble salts. I'm not going to give you insoluble salts in this section. We'll do that next chapter. These will be soluble salts, and we assume that they completely dissociate into ions. So this will happen 100%. We will form sodium ions and chloride ions. Okay? Same thing for sodium fluoride, 100%. Sodium ions and fluoride ions. Okay? And same thing for ammonium chloride. Soluble salt, completely dissociate into ions. Okay? So this is what we have to focus on, the products. We have to focus on the products. Sodium chloride does not exist as an NaCl unit in solution. It exists as separate sodium ions, separate chloride ions. Same thing for sodium fluoride, same thing for ammonium chloride, separated ions. So we have to focus on what we have written on the product side. All right? So, first thing, acidic, basic, or neutral before we calculate the pH. So we're going to try to predict, will these be acidic, basic, or neutral when dissolved in water? And then second, we're going to look at how do you calculate the pH. All right? If it's neutral, we don't have to calculate the pH. But if it's acidic or basic, we do. All right? So, first thing to look at, metal cations. Let's start with those. Okay? So metal cations can be acids. All right? But the ones that are typically acids are highly charged, and I'll show you what I mean by that, and small. Okay? So highly charged cations that are small, something like aluminum 3 plus, okay, in solution. That can actually function as an acid. All right? And so we're not going to focus on metal cations very much. For our purposes, I'm not going to give you any metal cations in these salts that are acids. Alkali metal cations, and alkaline earth metal cations they are not acids in water. Okay? So what that means is if you have a salt that has an alkali metal cation or an alkaline earth metal cation, we can ignore those ions. They aren't going to impact the pH of the solution. Okay? So in those first two salts, then we know sodium is not going to change the pH of the water. But what about chloride and fluoride? Okay? Well, let's take a look. And we'll look at that anion and we'll say, or we'll ask the question, what is chloride the conjugate base of? And we'll do the same thing for fluoride. Okay? So that was why, earlier in the chapter we focused a little bit of time on making sure you knew what a conjugate acid and conjugate base were and what a pair is. So the conjugate base will accept an H+. Okay, so if we add an H+, remember a base is a hydrogen ion acceptor, and so the acid that conjugate base comes from, chloride comes from HCl. Fluoride comes from the acid HF. All right, does everybody see what I did there? So you look at the anion, chloride and fluoride, and say, well, what acid do those come from? Okay, HCl and HF. Now, do you notice a difference between those two acids? Is there any difference between those two acids? Okay, one's a strong acid, one's a weak acid. Okay, now let's pick HCl and let me write out a few reactions here. And let's write out HCl functioning as an acid, as it is, in water. Producing hydronium. Acids produce hydronium. So when HCl donates the H+, that would then give us the conjugate base. Okay? So that's what we expect to happen, HCl dissolved in water. But let's look at the reverse. What would chloride do in water, the conjugate base? So chloride is the conjugate base of HCl. That could accept an H+ to produce HCl and hydroxide. Okay? So two reactions. One as HCl functioning as the acid. The other, its conjugate base, functioning as a base. Okay, bases produce hydroxide. Now, we can write a Ka expression for the first one. You should be familiar with all of this stuff. I'm just cranking along here. Hope you're hanging with me. And we can write a Kb expression for the second reaction. Oops, why did I put Cl minus up there? Sorry about that. HCl is the product. Hydroxide is a product over chloride. We don't include water. Now, what happens if I multiply Ka times Kb? And you're going to say, why are we doing that? Hang with me. So take Ka times Kb. So there's my Ka expression. Here's Kb. Hopefully I'll write everything in the correct spot as I continue. Okay, so what do we notice? HCl in the numerator, HCl in the denominator, cancels out. Chloride in the numerator, chloride in the denominator. So all we're left with is H3O plus times OH minus. Okay, so you're like, Dr. C, why did we just go through all of that? Well, think about, what does H3O plus times OH minus equal? Hopefully you're thinking. That is our KW expression. Okay, so look back. KW is equal to H3O plus times OH minus. So that leads us to this equation. Okay, so KW is equal to the Ka for the acid part of the pair times Kb for the base part of the pair. So we're always talking about a conjugate acid-base pair, like HCl and Cl minus, as we just wrote. Okay, so that Ka is not just any Ka, and that Kb is just not any Kb. It's for that conjugate acid-base pair. Okay. All right, I'm going to get rid of the red. I don't like writing with red for too long. All right, so that's going to be important. So, as an example, the Ka for HCl is about 1 times 10 to the 7th. Strong acid. Almost completely ionizes. All right, we've talked about that. So if we take our Kw, it's equal to Ka, and we want to then solve for Kb for chloride, the conjugate base, what do we get? Wow, look at that number. That's a really, really small number, meaning that chloride is not a base. Okay? It's so weak. It's a weaker base than water. Okay? It's not going to function as a base in water. Not a base in water. Not going to happen. So, conjugate bases from strong acids do not function as a base in water. So let's write that down. Conjugate base All right, lots of stuff. We've kind of covered all this stuff this chapter. We're now putting a lot of pieces together. All right, so conjugate base from a strong acid does not function as a base. So what does that mean for, and you might forget where we started, and I'm not going to scroll up, but we started with sodium chloride. Hopefully you're taking good notes. Look back in your notes. So we predicted that sodium ion was not an acid. Okay, and we just went through a lot of stuff here to figure out that chloride was not a base. So what does that mean in terms of the pH of that solution? Sodium chloride dissolved in water. Well, if sodium doesn't impact the pH and chloride doesn't impact the pH, pH is going to remain neutral. All right, and at 25 Celsius, that neutral pH is 7. All right, so boy, look at all the stuff we have to think through. Cations, if they come from an alkali metal, if there's an alkali metal cation, alkaline earth metal cation, those are not acids. Conjugate bases from strong acids are not bases. All right, and one thing you might want to keep in mind for the conjugate base, the stronger the acid, the weaker its conjugate base. And we just saw that up here. Really strong acid has a really big Ka, meaning the Kb value for the conjugate base is going to be really, really small. Stronger the acid, the weaker the conjugate base. And this conjugate base is so weak, it's not going to produce any hydroxide in water. Don't have to worry about it. All right. A lot of stuff to think about. Now let's compare that to sodium fluoride. We already decided that sodium ion was not an acid. But what about fluoride? It is the conjugate base of HF, which is a weak acid. Okay? So now things are going to be a little bit different. If it's the conjugate base of a weak acid, it's going to have some base strength in water. It will produce some hydroxide. And if you want to do a calculation, because we're going to need that to calculate the pH, Okay, again, we're focusing on 25 Celsius, kW 10 to the negative 14th. Ka for HF is equal to 7.1 times 10 to the negative 4th. So we solve for the Kb for fluoride. Let me grab my calculator here real quick. I'm going to carry one more sig fig, 1.41 times 10 to the negative 11th. All right, so what does that mean? You look at that number and you say, well, that's still a pretty small number. But compare that to the Kb for chloride. And let me scroll back up. It disappeared. There it is. 10 to the negative 21st. This one's 10 to the negative 11th. It's 10 orders of magnitude. Okay, 100 billion times larger, that Kb value for fluoride. So fluoride, being the conjugate base of a weak acid, will function as a base in water. Okay, it's still a weak base. Okay, as you can see by this Kb value, still quite a weak base, but it will produce some hydroxide. And sodium fluoride, that solution will then be basic. Okay, so the conjugate base of a weak acid is a base in water. Everybody get that? Conjugate base of a weak acid is a base in water. Okay, so let's actually now do the second part. Since we've already figured out that fluoride is a base, let's actually calculate the pH of a sodium fluoride solution. So say that we had 0.1 molar sodium fluoride. Okay, when that ionizes to sodium ion and fluoride ion, remember that goes 100%. Okay, so all of that's going to dissociate. We're going to get 0.1 molar sodium ion, and I just added an extra sig fig for some reason, and 0.1 molar fluoride. Complete ionization. Okay, so we don't have to worry about sodium, but we do have to worry about fluoride. Right? So what is fluoride in water? It's a weak base. So we have to write that reaction. What is a Bronsted base? Hydrogen ion acceptor. Let me write my AQs in here. Producing HF, the conjugate acid, and bases produce hydroxide. All right? So you should know how to write these things. I do use equilibrium arrows because this is a weak base. We're not going to get that much hydroxide, but we will get some. And if we get some hydroxide, the solution will be basic. All right? And so initial, here we go, ice tables, they won't go away. Still with me? This is lots of stuff. Again, when we get back after spring break, we will review this stuff some more in class. It's not like this will be the only time you'll see salts. But I want you to start practicing on these, do some problems, and we'll do more of this after spring break. Kb expression, remember this is a base, it's Kb. Products over reactants, not including water. We solve for the Kb value above, so you're typically, some some tables you'll look up, you might find the Kb for fluoride in a table, but more likely than not, you're going to find the Ka for HF. And just as we did right here, right, you can then use that expression Kw is equal to Ka times Kb to solve for the Kb for fluoride from the Ka of HF, okay, from the conjugate acid. Okay, so you might have to do that quite often. So we solve for the Kb value, 1.41 times 10 to the negative 11th. X times x squared, over 0.1 minus x. Sorry. What assumption can we make? This is a really weak base, so x will be small. Okay, compared to 0.1. Cross multiply. Take the square root. I lost 1.41. So X is 1.187 times 10 to the negative 6 molar. And what does that equal? Is it hydronium? Is it hydroxide? What is it? Look at your table. X is hydroxide. Fluoride is a weak base. We already predicted it was going to produce a basic solution. Bases produce hydroxide. Okay, so this is hydroxide. Take the negative log of that number to get the POH. My number of sig figs keeps growing. Okay, pH 8.075. I'm really sorry. I don't know what's going on here. Hope I'm not getting sick for spring break. That would not be good. All right, there you go. Now, technically, since it was 0.1 molar, typically, since this has 2 sig figs, when we do pH, we're supposed to carry 2 digits after the decimal point based on this number of sig figs we have. It's different than normal sig figs, so we really should express this as 8.08 to match the 2 sig figs, in this case, after the decimal point. Not real picky on sig figs for that. Is this a weak base? Fluoride, is it a weak base? Yeah, it's a really weak base. Okay, it is basic, but it's only pH 8. Pretty darn weak base, as you would expect by that Kb value. All right, hope you're still with me. The battery on my microphone is dying. I better get going. We have one more salt to do. And if you remember, that was this salt. Now, sometimes with these conjugate acids from weak bases, so this is the conjugate acid of a weak base, I'll help you out a little bit a lot of times and put a positive sign by that to help you see that that's the cation part of that salt. Takes a little practice because we're so used to looking at metal cations. These conjugate acids from weak bases, looking at those as a cation is going to be a little confusing at first. But that salt will completely dissociate into ions, forming the cation and the anion. Now, we already talked about chloride. Conjugate base of a strong acid, HCl. That has no base strength in water. Not a base. But what about ammonium? As we said, it is the conjugate acid of the weak base, ammonia. Okay, so kind of like what we saw, conjugate base of a weak acid was a base, so fluoride was a base. Same thing here, conjugate acid of a weak base will be a weak acid. Okay, so if it's the conjugate of something weak, weak base or weak acid, it will have that property. Conjugate acid of a weak base is a weak acid. So this is an acid, so what do we need? Well, let's write the reaction first, and then we'll talk about what we need to go on. So this is a weak acid, ammonium. What do acids do in water? Hydrogen ion donor to produce hydronium. And what else? The conjugate base. Okay? So you will always see the pair on opposite sides there, as you might expect. So let's do 0.1 molar. So again, if we start with 0.1 molar ammonium chloride, it completely ionizes. We will produce 0.1 molar ammonium. That will be our initial. No product to start. Change minus x plus x plus x. Okay, so that's standard looking ice table. All right, this is an acid. We write the Ka expression. Ka for acids, Kb for bases. What's the Ka value? Oh, it's not given. Most likely, if you go to look it up, you might find it, but you might not. More likely than not, you'll find the Kb for ammonia to be 1.8 times 10 to the negative fifth. So how do we get the Ka? Okay, so I just rearranged that Kw is equal to Ka times Kb. So the Ka will be Kw divided by Kb. And so take 1 times 10 to the negative 14th. 1.8 times 10 to the negative fifth, divide by that. See what we get. Here's 5.56. 10 to the negative 11th, I believe. Ten to the negative 10th, sorry. 5.56 times 10 to the negative 10th. Okay? That's still a really small Ka. So by no means is ammonium a strong acid. It's still a really, really weak acid, but it is an acid, and it'll produce some hydronium. It will make the solution acidic. So this will be an acidic solution. We had already predicted that the conjugate acid of a weak base is an acid, so this will be an acidic solution. Let's calculate the pH. So we now have our Ka. X times x squared over 0.1 minus x. Can we make an assumption? Yeah, this is a really small Ka value. So x will be really small compared to 0.1. Okay, this should still look really familiar. There's just a lot of new pieces to put together here, but the calculations and the ice tables and all of that are the same. You just have to know what reaction to write out, so you're going to need to practice that. So we cross multiply, take the square root. I get an x value of 7.457 times 10 to the negative 6th molar. And what is x? Hydronium? Hydroxide? This is an acid. Acids produce hydronium. So this is hydronium. Take the negative log of that, get the pH. pH is 5.13. Is that an acid? Yeah. Okay. Not a strong acid. pH is less than 7. The solution is acidic. It is a weak acid. It's quite a weak acid, 10 to the negative 10th. It will give us an acidic pH, but it's going to be a higher pH than, say, our typical normal weak acid or a typical normal weak base. This is a really weak acid. All right, so let's review here real quick and wrap this up. I'm going to go all the way back to the top. So, salt solutions. We're only going to deal with soluble salts right now. Soluble salts will completely dissociate into ions. So remember, you're dealing with your cation and anion from that salt. You have to look at each of those and predict, typically, is the cation an acid? Is the anion a base? There are exceptions to that, but for the most part, that's what we'll do. Cations, is that an acid? Anion is a base. Don't worry about alkaline metal cations or alkaline earth metal cations. Those are not acids. For the conjugate, the anion, if it's a conjugate base of a weak acid, it is a base. Still a weak base, but it is a base. Conjugate base of a weak acid is a base. However, if it's a conjugate base of a strong acid, it is not a base. Watch out for these cations that come from a weak base, the conjugate acid of a weak base. Those are going to be hard for you to recognize initially. But if it's a conjugate acid of a weak base, that is an acid, as we just saw. Okay? So you do have to be able to just look at a salt solution and predict, is it acidic? Is it basic? Is it neutral? Next, you do then have to be able to calculate the pH. So you have to then, like we predicted, fluoride was a base. We have to write that reaction as fluoride as a base. All right? Then you also have to write the reaction, if it's an acid, ammonium, write that as an acid. Let's scroll down and look at those setups. So let's do fluoride first. So we determined fluoride was a weak base. Bases accept a hydrogen ion. You're going to produce the acid part of that conjugate acid-base pair, but more importantly, bases produce hydroxide. We set up our standard ice table. solve for x. I'm just going to double check this calculation here because it seems like a really small p, or it's low base. I mean, it should be small basic, but 8 seems really low, but let's just double check that. No, that's why I got the same answer again, so hopefully I did that right. Watch out here. Since this is a base, when we solve for x, x is our hydroxide, so we take the negative log of that first to get the POH, and then pH plus POH is equal to 14 to get the pH. Okay? Now, ammonium is the conjugate acid of a weak base, so it's an acid. Acids are hydrogen ion donors, producing hydronium, and then the base part of that conjugate acid-base pair. Set up our standard ice table, standard Ka expression. Remember, quite often you'll have to get the Ka potentially from the Kb or vice versa. Kw is equal to Ka times Kb. We get that, solve for x. In this case, since ammonium is an acid, when we solve for x, we get hydronium directly. Take the negative log to get the pH. Okay, lots of stuff. Lots of stuff. All right, work on this. There will be a quiz in Sapling that you do have to complete before class Monday after spring break, and then we'll do some more salt solution stuff in class. But please practice some of these before class so that you really are prepared. Students always struggle with salts because we're taking concepts of equilibrium and ice tables and all that stuff that we've practiced, but now we're changing it up. In salts, you first have to look at, do you have anything that's an acid or a base? And if you do, you then have to write out the correct reaction and then set up your ice table and solve. Practice, practice, practice. Okay, have a wonderful spring break. Have fun. Come back ready to do some more chemistry. Hope to see you soon.